Alright, so this is the last part of the I2C communication protocol, or the two-wired interface, or the I2C bus simply. So we've seen that the I2C protocol is actually a multi-master, multi-slave, and only the master or the masters are allowed to control the bus, so initiate the transmission, terminate it, control the clock, etc. But the idea is, what could happen if two masters are attempting to control the bus at the same time without being aware that it's happening at the same time? So basically, each of the masters is checking the bus line, and they see that it's a free bus, and they're gonna attempt to start a transmission. What would happen then, right? So none of the masters are aware that another master is trying to control the bus. So we need to make sure that this is handled properly. So what kind of problems do we need to deal with in this case? Well, the first problem is we need to make sure that the clock is not acting weird, because each master is trying to generate the clock signals. So basically this could be gibberish, right? And on the second line, which is the data line, we need to make sure that there's no interference as well. Hence, the needed transmission or the needed data is being transmitted correctly, and there's no overlapping or transmitting gibberish. So on the clock line, we will talk about something that we call synchronization, and on the data line we'll talk about something that we call arbitration. Fair enough? So synchronization for the clock and arbitration for the SDA. All right. The best solution for lazy engineers is, instead of using the multi-master option, we can always use one single master in the system. Hence, we don't need to do any synchronization or arbitration. All right, so let's see a case study here. So you can notice how many masters represented in this schematic. All right, so basically we have clock 1, clock 2, and the SCL, the clock line of the bus. So basically we can assume that we have two masters trying to control the clock. So what would happen here? So apparently this one was the first one to bring down the line, because remember, when the clock is not used, when it's at rest, it will be maintained at 1. So this one, the first master, he's trying to bring it down, so he will succeed into doing that, and hence the second master will follow. Fair enough. However, the first master is attempting to bring it back up again, but nothing is happening here, because apparently the second master did not bring it up again, so it's still at 0. So we can deduce that both clocks seem to be ANDed logically together in order to get the SCL line, and it is the case. So synchro is a wired AND, and high to low is the fastest to bring, it follows the fastest master to bring it down, and then we will see what would happen for the low to high. So as said, in the low to high now, right, the master that needs to go back to high will be forced in a wait state until the other master, because of the logical AND, right, will be forced until the slowest master, right, so the master with the longest low, the slowest one, will bring the clock back up again. All right, so you can see that. So the fastest one to bring it down from 1 to 0 is gonna control it because of the AND again, and the slowest one to bring it back from 0 back to 1 is the one who's gonna control the high cycle of the period. We good? And hence This will allow us to synchronize all masters together. Fair enough? Alright, so that's the synchronization part. Now for the arbitration part. No master can transfer if it detects that the bus is not free. However, you can, see the problem happening. The problem is two masters, they're listening to the bus at the same time and no one is transmitting, so basically they're gonna assume that the bus is free. Fair enough? So they may generate a start condition without a delta time, so this is a time of the observation, so it doesn't really matter. Alright, with a valid start condition. So both of them are considered to be a valid start condition of the bus because of the propagation delays, etc. And we're going to see a schematic, it will be easier to understand. So the whole point of arbitration is to determine which master is allowed to continue. So it could be based on a priority scheme, right? And we're going to see how it's happening. Arbitration is done bit by bit. So remember, two masters are attempting to send data. Let me use a pen here. So let's say master 1 and master 2, 1 and 2 are they started with the start condition. Remember, I'm not going to re-explain what is start condition. And then they're gonna start transmitting some data. Say 1 1 0, whatever, 1 1 0, etc. etc. I'm gonna finish up the byte here. And this is for the acknowledgement, etc. Right, and this one as well is sending a 1 1 1 0 0 1 1 and 1 1, and for the acknowledgement as well. So how arbitration is done? It's done on a bit-to-bit basis. So what we're gonna do is we're gonna compare what we're trying to transmit to the outcome on the SDA line. Fair enough? So try to map what we learned from synchronization to here. So most probably in order to arbitrate, we're gonna use, arbitration is to try to play the referee between two different masters. So what would happen here is, if we apply the same principle from the clock synchronization mechanism, and if the two are logically ended together, this means that on the SDA line we'll see a 1 here. So none of the masters will recognize that another master is transmitting at the same time. Fair enough? Same for the second bit. What would happen here now? Because those two are ended together, fair enough, so the result on the SDA line will be 0. And it is at that particular moment, that master number 2 will see that although he attempted to send a 1, but he's seeing a 0 on the bus, this means that master 1 is the one who won. Alright? And you can see that if the change, the difference did not happen here, but it happened later, this means that the process may take a lot of time, so many bits, right? So they can even complete an entire transaction without any error because it's the exact same message that they're trying to send. They look like each other. Fair enough? However, when a master sees that that he has lost the arbitration, then it has to stop transmitting and by means of turning out the driver, so the transmission driver. Fair enough? And the master who won is the master that will complete the transaction. So let's see an example here, and this is exactly what I told you before. So this is the first off, let's guess how many masters are there in that represented in that schematic. So basically we're seeing two things here, so most probably it's two masters. Fair enough? And we're seeing the I2C bus here, so the SDA line and the SCL line. And we've seen that now the SCL line is synchronized using the mechanism that we talked about earlier, the synchronization mechanism. Alright, so here we can see a start condition for the first master. So on the high clock, I'm bringing down from high to low, and at the same time, within that delta, master number 2 is doing the same thing. So both of them, they've seen that the bus line is empty, so it was 1, right? empty and no one is sending anything, so they are attempting to start a transmission. And on the SDA line we can see that a transition happening, so we're all good. What would happen next? So let's see the first bit. So the first bit is only legitimate on the high period, or cycle of the clock period. So this one is trying to send a 1, this one is sending a 1, and the result is a 1 over the high period. So we're all good. None of them can say that they lost an arbitration. They do not see any difference between what they're attempting to send and the result on the SDA line. Right, so now next high, so both of them are trying to send a 0, hence they are seeing a 0, because remember this is a logical AND between the two, so we're seeing a 0, so we're all good. So they will continue transmitting. What would happen here now? So this one is attempting to send a 1, this one is attempting to send a 0, so 1 and 0, the result will be 0. So yeah, so this one will see that although I'm trying to send a 1, I'm seeing a 0 on the bus. This means that I lost the arbitration, I need to stop. And this one will continue. Fair enough? Alright. So let's talk a little bit about the communication. So remember the paradigm here is a multi-master, multi-slave. So one master can try and talk to different slaves. So we need a way to be able to identify the slaves. So in networks, generally speaking, what is the best way to identify a terminal or a module or an entity or a computer? It could be anything at all, a node. So we're gonna use addresses. Fair enough. And you can check this schematic for a second or two and try to deduce what is the address size that is used in the I2C protocol. So if we check here, maybe we have a keyword, an address, right? So we can see that apparently it's bits 1 to 7, hence we can correctly assume that the address size is on 7 bits. What? I remember that you told us last time that it's byte per byte. So yeah, so we have 7 bits for the address, an additional bit for something, and then remember there's an extra clock cycle for the acknowledgement, for the ACK, to see if the receiver and notably the slave is getting what's being sent or not. Fair enough? So what about that one? So exactly, we have 1 byte here, an extra cycle for the acknowledgement, but we're only using 7 bits of the byte and we have an extra bit here. So what would that be? Read and write. So remember, the only one who's allowed to initiate a transmission is a master. So the master is specifying a slave address, and then we're gonna start sending or receiving. So in order to know whether the master is a sender or a receiver, so a transmitter or a receiver, so we need to know whether it's writing data or reading data from the slave. Fair enough? So this is what that bit is all about. Read or write. Fair enough? So let's see. So the slave address is 7 bits plus the RW, the read or write. So basically if we have an RW equal to 0 here, this means that I'm not reading, I'm transmitting, I'm writing, right? Because it's W bar. Fair enough? And if I have 1, this means that I'm asking the slave to send me some data in the upcoming packets. Alright, so as any good network protocol, there should be some reserved addresses, and for instance something equivalent to the 255.255.255.255 in the IPv4 protocol, right? There's all zeros, and this could be seen as a high, as a cuckoo, as a broadcast to all the slaves that are out there. Fair enough? And you can see there are different combinations that are reserved for future purposes or different things. Doesn't really matter. What I however need you to notice here is the thing in red. And you can notice that it's the exact same slave address. However, there's only one difference, and the difference is the RW bit. So what would that be? And I'm giving you hints. So why would I have some kind of other broadcast, right? That I'm calling a start byte, by the way. Why would that be useful? Well, simply imagine that we don't have the module for the, a slave might not have the physical module for the I2C connector or the protocol. Hence, instead of making the slave listen to the bus all the time and losing a lot of CPU time, maybe, or we can use that particular address to say to a particular slave that, alright, so be careful, a transmission is bound to happen and you will need to send me some bytes. Fair enough? Alright, so let's see a couple of examples here. So here's a transmission happening. We have the start condition here. Then of course the one who initiates is always the master, a master, because there could be more than one master on the bus. And then we need to specify the slave address, the one that we want to talk to. And then here in that particular case, we're saying that we're going to transmit data from the master to the specified slave here. Fair enough? Then the slave will answer by an acknowledgement, and then I'm going to start sending the data to the slave, followed by an acknowledgement, 8 bits, etc. And here it could be either an acknowledgement or a NAC, a not acknowledged message. Fair enough? And the stop condition at the end. Alright, so this is one example of the transmission. Another example here, we have a master starting the communication, specifying a slave address, and then in this case, instead of sending data to the slave, I'm expecting to receive data from the slave. So I'm requesting some data from the slave by putting a 1 here, right? And then you can see that the slave says, okay, I got you, Holmes. And then the slave will start sending the data towards the master. Fair enough? And here you can see that the master is saying, okay, it doesn't really matter if it's a master. And then we have at the end the stop condition. Fair enough? Let's see a third and final example here. So we have the classical start condition, then a master is specifying a slave address. And here I don't really care if it's a read or a write. So if it's a read, the data will be transmitted from slave to master. And if it's a write, it will be from master to slave. But what I care about is what's going next. So alright, so these are the things that are happening. And then what do we have here? So you can notice that this is a repeated start condition. So you notice that the start was not followed by a stop. This means that for some reason the master changed its mind and now it's either want to talk to the same slave here and specify now that it wants to read or write. Maybe here it was trying to write and not read, right? Fair enough. So change the direction of the transmission or change the slave address, so talk to another slave. Fair enough? And then you get the follow-up and then the stop condition. Alright, so this is the end of it, and here you can see that there's an Arduino library for you to use if you want to use the I2C communication protocol. And in that case, I requested that you check it out before your tutorial, and it's your responsibility to go and see the different functions and how to use them, the different parameters, etc., as we did with previous protocols before. Fair enough? So thanks for listening, and see you soon.